In this video, we will briefly talk about antennas. So first we have isotropic antenna. Isotropic antenna is a concept that helps us to understand the behavior and properties of antenna. And this kind of antenna does not exist in reality, but it helps us to understand the system impact that these antennas will have. So it can be considered as a point source as described in the figure, and equal power is radiated in all the directions. So as a result, what we end up as is a sphere. Second is the omnidirectional antenna. Omnidirectional antenna is a dipole antenna of size lambda by 2, and in contrast to the isotropic radiator, which radiates equally in all the direction, the omnidirectional antenna have a pattern equal in the azimuth plane, whereas it is not equal in the vertical plane. So in case of isotropic radiator, if we assume that the radiated power is Pt, then the power flux density at radius r implies the total power radiated experienced in a unit area. It is given by Pt, that is the total power experienced in a unit area, given by 4 pi r square, and this is the surface area of sphere. Because isotropic radiator will form a sphere. So this phi r will represent how much is the intensity of radiation intercepted per unit area, and the received signal power is proportional to the effective area of the receiver. So this can be understood like this. If we have a transmitter and the signal is radiated and we have a receiver here. So how much power is intercepted by this receiver depend on the effective area of the receiver, and which in turn depend upon the size of the antenna, its cross-sectional area. So more the size of the antenna, higher the size of the antenna, or higher the cross-section area, the more power will be intercepted by the antenna. And also it is proportional to the orientation of the antenna. So what we mean by orientation is that if the antenna orientation is towards the base station, it will receive more power, whereas in the case if the antenna orientation is opposite to the base station, in this case the signal received will be very less. And in case of isotropic antenna, the effective area of the receiver is constant and it depends on lambda, that is wavelength. This is in meter, and lambda square we have meter square, and then area of the isotropic receiver is also meter square. So then received signal power is given as the multiplication of the power flux density and the effective area of the receiver. And then we get Pt upon 4 pi r by lambda whole square. And this is what is referred to as free space propagation, where we have a transmitter and a receiver, and we have line of sight transmission between the transmitter and the receiver. And the path loss in this case is given by Pt represented in dBm minus received power represented in dBm, and the difference of 2 dBm is dB, which is a dimensionless quantity. Now let us look at the example. Let's say we have an isotropic transmitter which is radiating equally in all the directions, and we have an isotropic receiver which is also receiving from all the directions. So now the transmit power is given by 100 milliwatt. This 100 milliwatt can be converted into dBW, and then we can add 30 to represent it in dBm. So we have 20 dBm. Fc is 800 megahertz, then lambda is 3 by 8 meters, and we want to see that what is the distance at which the receiver can receive a power equal to minus 90 dBm when 20 dBm is transmitted from the transmitter end. So now if you compute the path loss from the above expression, so this PT in dBm is 20 minus of 90, we have 110, and we substitute this expression into the path loss expression, and what we obtained is D is equal to 9.4 kilometer. So from here what we can what we can say is that if we have a transmitter and the signal distance D is equal to 9.4 kilometer, if the receiver is present at a distance of D is equal to 9.4 kilometer, we can expect a received power of minus 90 dBm at the receiver. And now when we decrease the transmit power, the distance is significantly decreased, and this can also be obtained from the same calculation as in the first example. And now D is approximately equal to 3 kilometer. And this is the case when we have line of sight expression or line of sight transmission when we have. But in reality, we do not have line of sight. We generally have multiple paths. So in case of multiple paths, this factor here in the free space propagation, this factor is generally not 2 but greater than 2. And as a result of which this distance will not be 9.4 kilometer but very less than 9.4 kilometer. Next is the omnidirectional antenna. Omnidirectional antenna is a dipole antenna of size lambda by 2, and it has a equal pattern in the azimuth plane, and it achieves maximum gain in the direction that is perpendicular to the dipole axis, and this is the dipole axis. So that means at 0 degree when the elevation is 0 and when the elevation is minus 90 degree, in this case there is hardly any gain in this direction. And this is the ideal pattern when we assume that there are no magnetic surfaces in the environment, but generally we have metallic surfaces, and when these kind of surfaces are present, then we can see there is some deviation in the azimuth pattern, and which is desired. So generally omnidirectional antennas are very common in handsets, in mobile phones. And why is this so? Because of the two reasons. First, we do not know in which direction the base station is and from which direction to receive the signal. And the second is, if we want to send the signal to the base station, we don't know where the base station is. So this omnidirectional antennas give us this possibility. Now, when we talk about base station, so base station generally provide patterns in a sector of 120 degrees. And this is a typical value in cellular system. So in base station, we generally use directional antennas, and directional antennas has a very specific radiation pattern. It is maximum in a particular direction, and as you go away from the direction, the gain will decrease. And we are always interested in what is the angle where the transmitter gain is between the maximum and the 3 dB gain of the maximum. That means what is the angle? Let's say this is the maximum gain and this is the 3 dB less than the maximum, and this is 3 dB less than the maximum. And this angle represented by theta 3 dB is known as the beam width. And generally we want this value to be equal to 120 degree to achieve sectorization. So now when the user is present in this direction, we can assume that huge gain is achieved in this direction, whereas as the user goes away, there is still some less amount of gain, but our aim is to further reduce these side lobes. Then the next we have effective isotropic radiated power. So this is the product of the transmitted power and the gain of the antenna divided by the feeder losses. What we mean by this is, let's say we have a power amplifier and the transmit power coming from here is PT. Then this is connected to the antenna. Antenna will have certain gain GT, and the connection is through the cables, and the cable will introduce certain loss, what we call it as this LF, that is feeder loss. This is generally due to the cables between the power amplifier and the antenna. And again at the receiver side we will have certain gain, and then we will have feeder losses and the signal will be received. So this GT will have a positive impact on this power, and LF will have a negative impact on the power. So what is achieved from this antenna after undergoing this process is known as EIRP. We can also understand this concept like this. If we have, let's say this is the power axis and this is PT. So PT is the power transmitted from the power amplifier. So first we will have a feeder losses which will decrease the power LF to certain value. Then we have gain of the antenna, it will increase the power gain of transmitting antenna. Then the signal will be propagated in the environment and we will have propagation loss. Let's say this is the propagation loss. It reduces the power significantly. Then we have gain of the transmitting antenna. Gain of the receiving antenna, GR. It will improve the power. And then we have feeder losses, LF again. So what is finally received is at this level. And let's assume that if this is the reference noise level, including the thermal noise plus noise figure, and this is given by C by N, which is also referred to as receiver sensitivity. And this is defined as the minimum power level required at the receiver to decode the signal correctly.